So I'll be presenting rocking drones with intentional sound noise on gyroscopic sensors. This is a paper presented at the USNIX conference by Yunmok Sun, Ho-Chil Shin, Dongkwon Kim, Yongsuk Park, Juwon No, Kibum Joy, Jungwoo Choi, and Yongdae Kim for the Korea Advanced Institute of Science and Technology. This presentation is for CS6263, Cyber Physical Systems and Design for Georgia Tech Fall 2019 semester, and my name is Camden McDonald. So this paper focuses on vulnerabilities in gyroscopic sensors from audible sound attacks. I'll get into what exactly a gyroscopic sensor is and the type of sound attacks that they're using in their experiments later on in the presentation. But the authors carry out these sensor spoofing attacks using microphones and speakers to attack gyroscopic sensors in what is called a sensor spoofing attack. And they were carried out specifically on MEMS gyroscopes. And we'll get into what a spoofing attack is, what a MEMS gyroscope is, and what the paper found later on in the presentation. So sensor spoofing attacks are an attack on a specific sensor, and it causes that sensor to output an incorrect reading to the system that is monitoring or watching for that sensor. So the sensor outputs a false sensor measurement, and the monitoring system or system that is reacting to that sensor output then could make a detrimental decision or not make a proper decision based on the sensor output that's been spoofed. And this paper specifically focuses on gyroscopic sensors. So in this context, the gyroscope is the sensor, and it is outputting an incorrect sensor reading to the monitoring flight control system on a drone. And obviously, an incorrect sensor reading from a gyroscope can cause terrible flight control decisions. So gyroscopes are a basic sensor device used for flight control in drones, as well as used for orientation in other electronic devices. So this paper focuses specifically on gyroscopes for drone flight control. So the gyroscopes output sensor readings for the X, Y, and Z orientation of the drone, or the pitch, roll, and yaw. And that tells the flight controller which of its four rotors to speed up or slow down in order to maintain a stable flight. So obviously, if you get incorrect sensor readings from your gyroscope, it could very likely lead to a crash as it speeds up or slows down the wrong rotor. This paper focuses more specifically on MEMS gyroscopes, so micro electrical mechanical systems. Like I mentioned before, they're commonly found in drones, including commercial drones, and some other devices you might have a use case for gyroscopes or smartphones or wearable healthcare devices. So MEMS gyroscopes have a sensing mass, and as the drone flies through the air, the sensing mass is pushed in the X, Y, and Z direction. And there are various sensing axes that pick up these movements in the mass and output the corresponding sensor readings to the flight controller. This paper focuses specifically on attacking the sensing mass by finding its resonant frequency. So if you can find the frequency that causes that sensing mass to naturally vibrate, then it can output incorrect sensor readings to the flight controller. So specific resonant frequencies are often unique to a particular gyroscope. And like I said before, this can cause incorrect sensor readings. They're generally inaudible, so above 20 kilohertz, but the paper did find that this wasn't the case for all commercial gyroscopes. There were some that had resonant frequencies in the audible sound range. So when the authors went to attack these sensing masses in the gyroscopes, they first needed to find the resonant frequency, and it was an exhaustive search. There's no way to know what the gyroscope's frequency is ahead of time unless it's given by the manufacturer, which is not always the case. And even if it is given by the manufacturer, it doesn't necessarily mean that that frequency is actually correct, as they found in their research. So they scan over a frequency using a single tone to figure out what the resonant frequency is, what frequency is causing the MEMS gyroscope to vibrate in its sensing mass. And once they've found that, they can use that frequency to attack the sensing mass. So obviously an attacker would either need to know what the gyroscope frequency was ahead of time, or have to broadcast attacks across a broad frequency band in order to be successful. So in order to set up the experiments for attacking these MEMS gyroscopes, they created a Python script to generate this exhaustive search single tone in order to find the resonant frequencies. They played these tones over a regular consumer grade speaker, 10 centimeters above all of the MEMS gyroscopes in the experiments. They used 15 different MEMS gyroscopes, and they were all available for sale to the general public or for commercial applications. They were set up using a simple Arduino circuit. So in order to actually implement attacks on the gyroscopes, they did have to connect them to some simple Arduino boards in order to get them to output their readings. And then this Arduino board was hooked up to a laptop that could measure the sensor outputs so that they could record how their attacks were actually influencing the sensors in the gyroscope. And when they were doing these attacks, the way that they measured the sound waves that they were attacking the gyroscopes with was through their sound pressure level. And the sound pressure level was measured using some professional equipment and a microphone. So this was the first experiment, and these are the results from the experiment. So they have the 15 different MEMS gyroscopes that they were attacking, the vendor or manufacturer, the number of axes that the gyroscope measured, and whether it was a digital or analog interface. The resonant frequency in the datasheet, so sometimes the manufacturer does give you the resonant frequency of the gyroscopes, and if they did, then it was given here in the table. And then the resonant frequency that the experiments actually found are on the right-hand side. So you can see that even though the manufacturer did give some resonant frequencies, they were not all found in the initial experiment. The 7 frequencies that were found indicate that there is definitely potential for attackers to be able to exploit this, given that almost half of the gyroscopes had a fairly easily findable resonant frequency. And it should be noted that by the paper's authors that just because the resonant frequency is not found in this experiment doesn't mean that it doesn't exist. They only scanned over a specific frequency range, and it could exist outside of that. So the authors built 2 do-it-yourself drones for the experiment. They were equipped with the L3G 4200D and MPU 6000 MEMS gyroscopes, respectively. The details of the drones can be found in the below table for frame size and propeller size and the software they were running for their flight controllers. Both the drones had their proportional integral derivative controllers calibrated for stable flight before the experiment took place. This was obviously for experimental integrity to make sure that any attacks that caused the flight control to become unstable were actually from the attack and not from an incorrectly calibrated PID controller. The algorithms used for converting the gyroscope readings through the PID controller to the flight controller are detailed in the paper, but are left out of this presentation for brevity. For the experiment attack setup, a small Bluetooth speaker was attached 10 centimeters above both of the drone's gyroscopes, and the attacking speaker played the resonant frequency of the gyroscopes found in the initial experiment while the drone was hovering stably in the air. So the attack caused target drone A to crash, and target drone B managed to maintain stability, but its gyroscope was affected. It's just only on the Z-axis, so that didn't cause the drone to crash, but did cause incorrect sensor readings as well. The results of the two attacks are detailed in the table below. The sound pressure level that the attack was generated at and the resonant frequency, and which axes were affected by the actual attack. So those are the axes that output incorrect sensor readings from the attacking gyroscope. So target drone A was obviously not able to maintain stability. They even tried the attack while the drone was slowly increasing its throttle, so accelerating towards the sky. Even under power, the attack still caused the drone to lose stability. So this initial experiment showed that there is the potential for gyroscopes to be attacked by outside sound sources, and the authors concluded that more research was required to fully understand the susceptibility of the gyroscopes to these types of attacks. So the last experiment that the authors ran was to test how far of a distance these attacks could be done from. And in order to do this, the authors linearly scaled the vulnerable gyroscope's outputs in relation to the sound amplitude and pressure level. And from this result, they concluded that the attack could be generated from as far as 37.58 meters if an attacker was to use a sound source that could generate 140 decibels of sound pressure level at 1 meter. So after the authors showed that the attacks are possible, they theorized a couple of attack scenarios. So one option is a attacker could hack a drone's onboard speaker if the drone has an onboard speaker, and cause that speaker to output resonant frequencies of the drone's gyroscope, and possibly resulting in a crash, as shown in the experiments. Another option is drone-to-drone attacks, where a drone could fly towards another drone and launch a sound attack that did not affect that drone's gyroscope, but affected the target drone's gyroscope, causing the drone to fall from the sky. There could be long-range acoustic sound attacks. There are long-range acoustic devices available today on the commercial market that can be used to focus sound at longer distances. And another thing that the authors theorized is that drone sonic walls could be set up to actually control restricted flight areas where the resonant frequencies are broadcast around a specific area in these pseudo walls, and any drones crossing them would be caused to crash if the resonant frequency of that drone was being broadcast by that sonic wall. So that would be a way to restrict flight in certain areas. So some of the countermeasures and defenses for the types of attacks that they tested would be physical isolation of the gyroscope. So one example, the authors note for the iPhone 5S, which is equipped with the L3G 4200D gyroscope, it would not be affected by the attacks that they actually tested because of the compact casing in the hardware circuit. Foam would also be another way to physically isolate the gyroscope. It's inexpensive, and foam that's 1 inch thick has approximately 128 decibels of insertion loss in sound pressure level, according to the findings of the authors. And so physically isolating the gyroscope, such as the iPhone 5S's gyroscope, or surrounding with foam, could potentially deter attacks. Another method for deterring attacks would be a differential comparator. So using two gyroscopes on a single drone, both with different resonant frequencies. If the resonant frequencies of one of your gyroscopes was detected, the drone could switch to the other gyroscope for sensor measurements. So even if one was successfully attacked, it would have a backup gyroscope giving it correct measurements. And another option is resonance tuning. So you could add an additional capacitor to the gyroscope sensing electrode, and you could use this capacitor to tune the resonant frequency of your gyroscope. This one is a little bit more problematic, as the authors note, given it could raise temperatures of the board or cause issues with other electrical components by adding this additional capacitor. But again, you could tune the resonance to be in a very specific frequency zone or completely inaudible zone if that was the goal. So to conclude the paper, the authors found vulnerabilities in 7 of the 15 gyroscopes. So they were able to find the resonant frequencies of 7 of the 15 gyroscopes. And they proved that attacking these gyroscopes with specific resonant frequencies, just using a small commercially available speaker, can cause the drones to crash. And simulations were carried out over larger distances to show that these attacks could be successful from quite a large distance. So other related work that's been done on gyroscope vulnerabilities include hacking smartphones. So mentioned in the paper is another paper that theorized a user's password could be stolen by monitoring a smartphone's gyroscope, because the gyroscope returns the vibrations and tilt and orientation and rotation as a user inputs their password. You could use some kind of algorithm to reconstruct the user's keystrokes based on the vibrations and tilt and movement of a smartphone as they input that password. Another theorized vulnerability for gyroscopes is an attacker could use a gyroscope to measure vibrations from people talking, so vibrations from sound waves from someone speaking, and use those gyroscope measurements to reconstruct a conversation that the gyroscope measured. So for example, a smartphone could be hacked, and the gyroscope's readings in that smartphone could be used to reconstruct a conversation that someone had around that smartphone. So thank you for watching. This concludes my presentation on rocking drones with intentional sound noise on gyroscopic sensors paper.